Now that most of the important pieces are in place, I can begin to assemble the serious results, the meaningful results, the results that most likely are the reason you're taking this class. I'll begin with line integrals. So this requires a bit of setup. First, let C be a plane curve. So by a plane curve, I mean a plane curve or a curve inside of R2 given by the parametric equations. X is x of t and y is y of t, where, say, t ranges throughout or is between a and b. Equivalently, of course, I can say that C has vector valued function or position vector. R of t is x of t I plus y of tj, again subject to the restriction that t lies between a and b. It is important, however, that I mention that this parametrization traverses the curve only once. So, for example, if it's x is cos theta or cos t, y is sine t, I want t only between 0 and 2 pi. So let C be a plane curve given by these parametric equations, or vector valued function, or position vector, where C is traversed exactly once. I can then roll out the following theorem, namely what is called the line integral of the function, say f of x, y, I'll generalize to 3 variables later, along the curve C is given as follows. Namely, the integral, and it's written over C to indicate that I'm integrating along the curve C, of f of xy ds, I'll come back to that s in a moment, is equal to the integral from a to b of f of x of t y of t times the square root of dx dt squared plus dy dt squared dt. All right, it's a bit of a mouthful. Let me put the pieces together. The first item is that hopefully you see I'm going from an integral over C to a familiar type 1, Calc 1 type integral. So first I should mention, I'll sort of enumerate these. This ds, another way of saying this integral, is that I'm integrating with respect to arc length. That's what the ds means. So this means integrating with respect to arc length. Somewhere around, I think, chapter 11 of the book, when we talk about parametrization, there is sort of following, I should put this in note 2, that S of t generally is the notation reserved for length of an arc C. So S of t equals the length of, I think there they call it the curve, but it's either the arc or the curve C, between r of a and r of b. Of course, those are the endpoints if I use the vector valued function interpretation of this curve C. So if S of t is the length of the arc or the curve C, given by r of t between r of a, or when t is a, and r of b when t is b, then I get that ds dt is equal to the square root of dx dt squared plus dy dt squared. Another way of saying this is that ds is equal to the square root of all of this stuff times dt. So that's what this is. Namely, first, you're integrating with respect to arc length. That means that the ds is replaced with this massive thing over there. I suppose I should sort of put that the zeroth or obvious step is that you replace x and y with x of t and y of t. I'll get to that in a moment. And then I suppose a final third remark, though it's really not a step, but does bear mentioning, is that the challenge here, so far I've just laid out a formula, is to rewrite everything in terms of the parameter t. So rewrite everything in terms of t. So from the top, at this point it's just a formula, but let me roll through it. I begin with a curve C. That curve has parametric representation, x of t and y of t, or if you like, vector valued function, r of t is x of ti plus y of tj. T ranges between a and b. That's the same thing as saying that r of t lies between r of a and r of b. Actually, I should be a little bit more cautious because these are vectors, so inequalities isn't quite the right thing to say. I should rewrite it as r of t goes from r of a to r of b. All right, so a parametric curve in the sense of Math 231, Chapter 12. And now defining this thing called a line integral. Don't yet worry what it is. The formula is the line integral along C of f of x ds. What does the ds mean? It means that I'm integrating with respect to arc length. Namely, I'm taking this new kind of integral called a line integral. What is this line integral? It's this thing here, where 0th step I plug in x of t for x, y of t for y, and the ds becomes this square rooty thing. A couple of remarks. First, saying line integral is the same thing as saying integrating with respect to arc length. Second, in case the notation is a bit confusing, the ds, I think it comes from chapter 10, where parameterization is first introduced. S of t is usually used to denote the function of arc length between, say, r of a and r of b. So that means ds dt is this square rooty thing. It's why this gets plugged in there. And then finally, usually, solving these problems amounts to rewriting everything in terms of the parameter t. The natural question at this point, I think, is something like, so what? Who cares? What is this thing called the line integral, and why bother? Well, it's a lot of things, but I'll begin simple. I'll begin with a basic geometric interpretation of this thing that I've introduced called the line integral of the function f of xy, or equivalently, the integral of the function f of xy with respect to arc length. Geometrically, this integral is the area under the function f along the curve C. This needs a bit of explanation. So, specifically, let me get this just so. Yeah. This guy, I'll go there. Cool. And this guy will look like there. Okay, the orange is the curve C. The green is the value of the function z is equal to f of xy that lies above C. So you can think of the line integral as the sort of area of this fence here. Namely, the area technically of one side of the fence, you don't want to count it twice, is going to be the integral along C of f of xy ds. This turns out actually not to be entirely unfamiliar. It's actually a generalization of something we've had for a long time. To make this clear, consider the following special case of this line integral that I've only just a moment ago defined. The special case where C is the line segment in R2, but from just A0 to B0. So it's from the x-intercept A to the x-intercept B, all the while y is 0. In this case, C has parametric equations. Well, y will always be 0, and x will go from A to B, so I can say x is t, where t lies between A and B, and y is 0. Well, I don't need any bounds on that. In which case, this gets me a bit more. This tells me that dx dt is not 0, but 1. And this, of course, tells me that dy dt is equal to 0. So what? Let me roll out once more my equation for a line integral of a function along a curve C. Namely, the integral along C of f of xy ds is the integral from A to B of f of x of t, y of t times the square root dx dt squared plus dy dt squared dt. So it's my sort of first instance of parametrizing, granted an awfully simple curve. In this case, I'll, let's see, have x will just be, well, the same thing as x or t. This will be 0. Dx dt is just simply 1, so it'll be 1 squared. And this will be 0 squared. So if you like, I guess I can call this, just to keep the notation consistent, I'll call x of t, t, and then I'll move it back again. So this is the same thing as the integral from A to B f of t0 times 1, or the square root of 1, times dt. This f then is a function of just one variable, t, which is the same thing as x, integrated with respect to t, which is the same thing as x. In other words, this is the integral from a to b of f of x dx. What I've said abstractly is that in the special case when it's a line segment along the x-axis, then the line integral, or the general integral with respect to arc length, turns out to be, this special case, the good old-fashioned Calc 1 integral that you're familiar with. How come? Consider what I'm looking for in this special case. Geometrically, I begin at the point A0 and I end at the point B0. So the curve is just a subset of the x-axis. The value of the function I'm interested in then will be also values of the function that lie directly above the x-axis. Let me keep this color consistent. So, say for example, there and there. Accordingly, in this special case, I'm looking for this area. But again, because I lie entirely above the x-axis, I can look at this just in the x and f of, well, xy, but y doesn't matter, so x and y equals f plane, namely this thing, when viewed just above the x-axis, is now, let me extend this just a small bit. There, and I'll put A there, B there. This was the interval sort of in 3D perspective. Here it is just looking at the cross-section that lies in the X and the F range. And here then I get that, and, well, I can't draw it exactly to scale, but hopefully you get the idea. This is precisely this thing geometrically. Said differently, the area under this curve above the x-axis there is, of course, the same thing as the area under this curve above the x-axis here. Here it goes by this name, namely the integral of, or the line integral f of x comma 0 ds, but in this really nice case, it will reduce to the case, or the good old-fashioned case of the integral f of x dx. Evaluate, for example, the line integral of 2 plus x squared y along the curve C, where C is the upper half of the unit circle. All right, so first order of business is to parameterize C. Begin with C. Well, it's the upper half of the unit circle, namely this thing there. So I'll take x is cos t, y is sine t, and I need to restrict the bounds on t between 0 and pi so that I traverse C, well, exactly once. Then, let's see, this gets me the integral from a to b. In this case, a is 0, b is pi, to plus wherever there's an x, put a cos. Wherever there's a y, put a sine. So it'll be plus cos squared t times sine t, but of course we're not yet done. This needs to be times the square root of dx dt squared plus dy dt squared, all with respect to t. Anytime we make the transition from integrating with respect to arc length, s, to integrating with respect to the parameter t, we pop out this extra term. If you're curious from whence it comes, yeah, the answer, as usual, from Riemann sums. It has to do with these sort of extra diagonals that you get when moving from a generic arc in R2 to just a single segment of the interval in x, or in t. Okay, dx dt, I think pretty straightforward. Here, I'll get minus sine t, and dy dt is going to be cos t. It doesn't really matter too much because this will wind up being a minus sine t squared and then plus a cos t squared. Yeah, I suppose that's square rooted, but I'm taking the square root of sine squared plus cos squared, which is the square root of 1, which is again just 1. So this entire thing, 0 to pi 2 plus cos squared t sine t dt. This is now officially a straight up Calc 1 integral. I've taken this new thing that has, well, sort of a vague geometric interpretation and turned it into something familiar using, well, the formula and a bit of Calc 1. Specifically, this will be 2t using a bit of u sub. If I take, say, u to be cos t, and that will get me du will be minus sine t dt. This cos squared sine t becomes a minus cos cubed t over 3 on the bounds 0 to pi. All right, 2 pi minus cos, I'll do it all out for the moment, cubed pi over 3 minus quantity 2 times 0. Be careful because cosine of 0 is not 0. Cos cubed 0 all over 3. All right, so this is a 2 pi. Cosine pi is minus 1. Minus 1 cubed minus 1, but minus that gets me a plus a third. But then it's a minus, not quite, minus a third. So in the end, 2 pi plus 2/3. As usual, I want to extend what I already know to be true into, well, what I would like to be true. Specifically, recall from good old-fashioned Calc 1 that if I have, say, some interval AB that lies inside of the reals, and say C lies between A and B. So another way of writing this is that AB can be written as the union of the interval AC and CB. Then the integral from a to b of a function f of x dx can be written as the integral from a to c of that function plus the integral from c to b of the function. Geometrically, this is usually explained in terms of area. Namely, you've got, say, a function f of x there, there's a, there's b, somewhere in the middle is c, and the justification is that the entire area under f between a and b is the same thing as the area between a and c added to the area between c and b. Likewise, in chapter 15 of the book, we have that if, say, some region D inside of R2 can be written as the union of two intervals, say D1 and D2, then the double integral over the region D of a function of two variables with respect to a can be written as the double integral over d1 of f of xy dA plus the double integral over d2 f of xy dA. And of course this extends to solid regions in R3 if you can chop them up into pieces as well. So what should be true when we extend this principle to line integrals over curves? So specifically, theorem. If C is, technically it needs to be called a piecewise continuous curve. So is a, or I'll say piecewise smooth curve, is a piecewise smooth curve. Smooth means it's differentiable, or if you like, it really means that it just doesn't have any corners, but only by pieces. So, for example, a piecewise smooth curve can look like this. Say something here, and then there, and then there, and then there. So if this is C1, and I'll show the direction that it moves as t increases, and this is C2, and this is C3, and this is C4, then C, which is equal to C1 union C2 union C3 union C4. This just means C is the curve C1 followed by C2 followed by C3 followed by C4 is piecewise smooth. It's smooth in pieces, therefore piecewise smooth. All right, so the theorem says that if C is a piecewise smooth curve, for example, this, then I can extend this result to its equivalent for line integrals, namely the integral along C of f of xy ds is the integral along C1 of f of xy ds plus the integral along C2 of f of xy ds, plus you get the idea, the integral along C3 plus the integral along C4 of f of xy ds. So just as you could, or if you could break up an interval into pieces that connected nicely, you could then write the integral of the function as the integral over the pieces, or bump it up a dimension, the integral over the region as the integral of its pieces. So too, if C is nice just as more rigorously piecewise smooth, the integral over the curve is the integral over its pieces, provided it's piecewise smooth. Evaluate the integral, the line integral, of the function 2x along C, where C, I'll define piecewise, consists of the arc of the parabola y is x squared, just from the origin up to 1, 1, from 0, 0 to 1, 1, and I guess I'll call this arc of the parabola C1, and then followed by the line segment C2 from 1, 1, we'll move up to 1, 2. All right, so as usual when playing with line integrals, first order of business is figure the curve C. Parameterize, that is. So I need to parameterize first C1 followed by C2. I suppose before that even, what in the world does this look like? First I go from the origin 0, 0 to 1, 1. So this is C1, and then followed by C2. So there's 1, 1, and there's 1, 2. All right, I need to parameterize each piece, evaluate the line integral on each piece, and then add the results together. All right, so I'll begin here with C1. There are a number of ways to parameterize this. And if you feel uncomfortable with it, either revisit the section on parameterization, write me, or my lectures from 231 on parameterization. I took time out to do about an hour on it. Should hopefully clarify a lot. So let's see. I'm going to parameterize a bit differently than the book, just because I like using t as a parameter whenever I can. In particular, I'm going to choose x is equal to t, and y will then be t squared, because it's x squared. The bounds on this will have to be t is between 0 and 1. This will get me that dx dt is 1, and dy dt is 2t. All right, so what? This then says that the integral over c1 of 2x ds is the integral. Wherever there's an x, put a t. Wherever there's a y, put a t squared. So this will be 2 times, well, there's only an x, t, but in the passage from the ds to the land of dt, namely the passage from integrating with respect to arc length to integrating with respect to the parameter t, I need this square root sign. And in here I'll have dx dt squared plus dy dt squared, all with respect to t. The bounds are the bounds on t. This, I think, pretty straightforward. Integral 0 to 1 to t, and I wind up with a 1 plus 4t squared dt. I'm just plugging in the dx dt and the dy dt and squaring them under the square root sign. This is a cute bit of u substitution, namely if I take u is equal to 1 plus 4t squared, I'll wind up with du is an 8t dt. So this then gets me 1/4, to compensate for that 2, times 2/3 times 1 plus 4x squared to the 2/3 from 0 to 1. I don't have much room left, so I'll go right to the punchline. It's 5√5 minus 1 over 2. A note before I move on, I've done this differently than the book, generally because I like to parameterize in terms of t whenever I can. The book does the following. The book decides to take x to be the parameter, which is fine because x then in terms of x is x, and we already know that y is equal to x squared. However, this means that here, instead of a dx or instead of a dx dt, you'll wind up with dx dx because you're differentiating x with respect to the parameter that is itself, obviously squared. And here you'll wind up with a dy dx squared. And there you'll just leave the x as an x. Grind all this out, you'll wind up with the same result. I just like to sort of arbitrate everything to an independent parameter to keep track of what's going on. And of course, I mean, since x is t, the bounds on this parameter are also 0 and 1. All right, so that just gets me C1. I also need C2. Specifically, I need to begin with a parameterization of C2. I need to go from the point 1, 1 to the point 1, 2. X is always going to be 1, so I'll write x is equal to 1, and y will go from 1 to 2. So I'll say y is equal to t, and I'll put t between 1 and 2. Like I said, there are a lot of ways to parameterize this. You could use the old-fashioned trick from 12.5, or section 12.5, where you parameterize any line segment between t is 0 and 1 with a nice formula. We'll get to it soon enough. Or you could use, I think, the book. The book, I think, just uses parameter y here. But as usual, I like t when I can. So what does this get me? It says that dx dt is 0 and dy dt is 1. So what? The integral along now C2 of 2x ds, again, is the integral of wherever there's an x, now put a 1, and the square root of dx dt squared will be 0 squared. The square root of dy dt squared will be plus a, I guess, not very eventful, 1 squared. All of this integrated with respect to t. And of course, I'm on the bounds that bound the parameter t, 1 to 2. All right, so integral 1 to 2, 2 dt, 2t, 1 to 2, 4 minus 2 will be 2. All right, 2 of the multiple choice answers to this problem in the book, if it is in the book, I'm sure are this one A, this one B, neither of which are true, because remember, I'm integrating not along C1, not along C2, I'm integrating along C, which is made up of C1 followed by C2. So the integral along C of 2x ds is equal to the integral along C1 of 2x ds plus the integral along C2, 2x ds. That guy there, 5√5 minus 1 over 2, and then plus 2. Suppose, just to be exhaustive about this, you can again choose y as a parameter, in which case you have x is 1 and y is, well, y. In which case, dx dy will be 0 and dy will be 1. So 2x is still 2 times 1 because x is still 1. And this will be a dx dy squared, 0 squared. This will be dy dy squared, which is 1. I'm really just dotting i's and crossing t's here, but I want that so that the computation is straightforward, so that when we get to the heavier theory, this isn't too much trouble. I need to get technical for just a moment. Specifically, I began the discussion of a line integral of a function of x and y by integrating with respect to arc length. That's what the ds means. So here I am integrating f with respect to arc length. But I'm not restricted to just that case. Namely, I can integrate f of xy along a curve c with respect to, well, just x, or with respect to y. It looks like, say, for example, this. The integral of f of xy, if I want to integrate not with respect to arc length, s of t, but with respect to x, it won't be ds, it'll be dx. This is the integration of f with respect to the variable x. Likewise, I can integrate the function with respect to y. Then there'll be a dy. This is the integral with respect to y. Admittedly, at first, this seems like a bunch of abstract nonsense. Well, probably is a bunch of abstract nonsense until I explain it. For the moment, I think it's important to keep track of the integral with respect to x as adding up or accumulating f into the direction of x, whereas integrating with respect to y is accumulation as integral in the direction of y, and originally integrating with respect to arc length was along the curve c. All right, so how to evaluate. Turns out this part's awfully simple. To evaluate, as is usually the case whenever I need to deal with a curve C, write everything in terms of your parameter t. That means, for example, write x as a function of a parameter t. That will get me then dx dt is equal to the same thing as x prime of t, or, namely, this dx there, I can call x prime of t dt. Likewise, y will be written as a function of the parameter t, and this will say that dy dt, which is the same thing as y prime of t, can now be written as dy is equal to y prime of t dt. It looks like I am just sort of fiddling around with notation. Well, really, I am just sort of fiddling around with notation for the moment. Hopefully, two things. It's straightforward, and you get that, at the very least, this is a simplified version of what's up there. The x prime of t dt will stand in place of the square root of dx dt squared plus dy dt squared. Specifically, I get that, I'll stick here, the integral over c of f of xy in the direction of x is again going to be the integral from a to b, and again I'm going to replace x with x of t and y with y of t. So x of t, y of t, but now instead of the square root of the sum of the squares of dx dt and dy dt, I'll have just this guy, x prime of t dt. Likewise here, the integral along the curve C of f of xy dy will be the integral a to b f of that point, but now a y prime of t dt. And might as well put the original up here to keep track of everything in one place, although it's a bit tight. The integral of f of xy ds is the integral of f of x of t, y of t times the square root of the sum of the squares of dx dt and dy dt. Here, then, perhaps you see that if I'm just going along the x direction, everything with y zeroes out, or the rate of change, of y zeroes out, so y prime is 0, although y may not be 0. And in this case, since I'm just moving in the y direction, there's no rate of change of x, so the x prime zeroes out, so you just wind up with the square root of the square of y prime, or the square of x prime, and, well, it's just a long-winded way of saying you get back the formulas you have here. Finally, I guess a bit of notation makes following the book easier. I'll often write, for example, and as will the book, the integral of p of x, y, say as one function of x and y, with respect to x, plus the integral of another function of x and y, q of xy dy, to indicate that I'm integrating p along c in the x direction and q along c in the y direction. Specifically, this means the integral of p of xy dx along c and the line integral of q of xy dy along c. What does all of this abstract theory mean? The answer, not surprisingly, is, well, more abstract theory. So let me ground all of this in a very concrete example. Specifically, I want to evaluate a line integral. In particular, I want to evaluate y squared dx plus a x dy over a curve C, but I want to do it over two different curves. So evaluate the line integral y squared dx plus x dy, where C is, say, given by, on the one hand, C1. C1 will be the line segment, say from the point -5, -3 to 0, 2. And then I want to evaluate the same integrand, y squared dx plus x dy, but I want to integrate it over a different curve, C2. C2 is going to be a piece of the parabola. So piece of the parabola, x is equal to 4 minus y squared. And here again, I want to go from the point -5, -3 to the point 0, 2. All right, so as usual, I think it's a good idea to begin with some sense of what's going on. So minus 5, 1, 2, 3, 4, 5, and minus 3, 1, 2, 3 is somewhere around there. Whereas the point 0, 2 is about there. So label these accordingly. Here's the point 0, 2. Here's the point minus 5, minus 3. All right, the first curve, C1, is a direct line segment from minus 5, minus 3 to 0, 2. So first, C1 goes that way. The second curve, C2, is a piece of a parabola opening into the negative, or opening along the negative y-axis with intercept, I guess, 4. So it will look like, oh, I just missed it. There. So here is C2, and there's the x-intercept 4. So the task on the one hand to evaluate along C1, and on the other hand to evaluate along C2. First order of business for C1 is, I think, to, as usual, figure out how to describe it, namely, what's the parametrization. Here I need to bring back a trick from 12.5, I think is the section. So the section 12.5 trick. This is a handy thing to have in your back pocket. If you remember it from 231, great. If not, I might as well spell it out here because it's important enough and we'll use it often. The trick is to parameterize any line segment very nicely. Namely, I want to parameterize a line segment from, and I'll call it R of, or R naught, which is the position vector corresponding to the point x naught, y naught. And I want to go to R1, which is the position vector corresponding to the point x1, y1. So here I'm just writing a bit of shorthand. R0 and R1 are position vectors. Their tips are at the points x0, y0, and x1, y0. Sorry, their tips are, let me untie my tongue. The tips of the position vector R0 and R1 are at the points x0, y0, and x1, y1 respectively. Whew, that was a mouthful. In any case, to parameterize this line segment, I've got that R of t, the position vector for the line segment, is equal to 1 minus t R0 plus t R1. I can expand this as, say, the position vector of the point x of t, y of t. This then I can call x0, y0, and this I can call x1, y1. And under this parameterization, I need, or I get, the very handy restriction that t is between 0 and 1. All right, so in this instance, going from, say, minus 5, minus 3 to 0, 2, this says, so I've got that x of t will be 1 minus t times x0, where I begin, minus 5, plus t times the x where I end, 0. All right, well, this cleans up rather nicely. The second term obviously zeroes out, so I wind up with 5t minus 5. Similarly, for y, it's going to be 1 minus t, but I'll have y naught to begin with. This turns out to be a minus 3 plus t times, I guess where I end, at 2. So this will be minus 3, but then plus a 3t plus a 2. So what do I get? 5, hang on a second. No, yes, no, yes, yes, no, yes, yes, no, yes. There I am. 5t minus 3. Cool. All right, and of course here, again, this parameterization works for t is between 0 and 1. It's easy, as usual, to make arithmetic mistakes, so let's head back and check. At t is 0, I get minus 5 minus 3. Great. At t is 1, I get 5 minus 5 is 0 for x. Super. And 5 minus 3, 2 for y. Also super. All right, so then I need to evaluate the integral on this region here. And I'm going to try to keep everything in one space. So in order to do that, the integral along C1 of y squared dx plus x dy is going to be, well, I need to fill all this out. The integral 0 to 1 for the y squared, I put in the 5t minus 3 quantity squared, and the dx will just be a 5 because, well, derivative of 5t with respect to t is 5. So times 5 dt, but then I need whatever the x is, the 5t minus 5, then times the derivative of y with respect to t. Well, dy dt will also be 5, so dy is 5 dt. This cleans up as the integral from, let's see, 0 to 1. I guess I can pull a 5 out of this whole thing. No, I'll leave it as it is. 0 to 1 of 125 t squared minus 125t, and then plus a 4 dt. This is a straight up Calc 1 type of integral. I have room, I guess, for one intermediate step. This will get me 125 t cubed over 3, and then minus a 125 t squared over 2 plus a 4t on the bounds 0 to 1, and it turns out, if you look at it really hard, a minus 5/6. All right, so that's the integral of this thing, y squared dx plus x dy along C1. What of the integral not along C1, but along C2? We do this here, then. Specifically, again, I need to begin by parametrizing. I'm going to parametrize not a line segment, but a piece of the parabola. I think it's easiest to take y is equal to t, in which case x will be 4 minus t squared. Let me put this up for x. Here the bounds aren't 0 to 1. X is 4 minus t squared. Instead, here the bounds are going to be, t will be between, well, when y is down here at -3, and up here when y is equal to 2. So I've got bounds -3 to 2. All right, it's a bit more of an involved computation, but the principle is the same. Namely, the integral along C2 for y squared, I'll put in a t squared. dx will no longer just be a number. Instead, it will be derivative of x here, a minus 2t dt. And then plus for the x, I'll put in the 4 minus t squared. And then dy, the dt. All right, again, this is probably not the most interesting integral. I suppose I should also replace C2 with its bounds for t, minus 3 to 2. You get the idea. So at this point, one intermediate step. This will be the integral from minus 3 to 2, minus 2t cubed, minus t squared, plus 4 dt. I'll leave the rest of this to you. In any case, what's important here is that it comes out to a 40 and 5/6. What's interesting, I think, about 40 and 5/6 is that it is definitely not negative 5/6. So this is what I mean or meant by saying I want to get to even more significant theory, but I want to do it by way of an example. I did a line integral of the same function or integrand, y squared dx plus x dy, along two different curves. They begin at the same point and they end at the same point, but taking different paths seems to have changed the result. Specifically, it should be pretty obvious that the integral along C1 is absolutely not equal to the integral along C2. This gets me a rather important two-part proposition. Namely, in general, a line integral doesn't just depend on the endpoints. It depends also on the path taken. This wasn't a concern in Calc 1 because the only path you can take is along the x-axis. So let me summarize here. The integral along C in general of a function f of xy, this holds true for dx, dy, or ds, depends, one, you might guess, on the endpoints, but two, and perhaps much more importantly, depends on the path taken, i.e. the specific C. If you choose a line segment, it'll get you a different answer than if you chose this piece of the parabola. Even though you begin at the same point, end at the same point, and you're integrating the same thing. The path taken makes a difference. I want to begin by repeating what I concluded just a moment ago. So, a couple of remarks. Namely, that the line integral over a function, of a function over a curve C may depend on, well, obviously, one, the endpoints of the curve C, but it turns out may also depend on the path C itself. But it may very well depend on more than that. It may depend not just on the path C, but the direction that C is traversed. So I'll put this up as direction. So in the previous example, I had that C1 went from, say, 5, negative 3, to the point 0, 2. Using conventional notation, I want to be able to say, how do I go backwards? Namely, if C1 goes from -5, -3, to, how do I indicate the path backwards? Well, not surprisingly, it's called negative C1. Negative C1 goes from 0, 2 back to the point -5, -3. And there's a definition I can get out of this while I'm here. The direction has a very specific name. It's called the orientation. So, definition, the direction of a curve C is called its orientation. Not surprisingly, positive orientation corresponds to increasing values of t, whereas negative orientation corresponds to decreasing values of t. So, positive orientation corresponds to t, or the parameter, increasing, and negative orientation corresponds to the parameter, as you'd expect, decreasing. So these two, obviously here, this would be positively oriented, this would be negatively oriented, and while I'm busy defining a whole bunch of terms, these two have what's called reversed orientation. Here, C1 and C2 have reversed orientation. Something you, well, might expect. Let me consider this example of C1, or sorry, negative C1. Negative C1 goes from 0, 2 back to -5, -3. This will have parametric representation. Here I'll just cut right to the chase. X is -5t, and y will be 2 -5t. Not surprisingly, it's the parameterization for C1, just with negatives distributed through. So 2 -5t, and again, of course, t is between 0 and 1, in which case I wind up with the integral along C1 backwards, negative C1 of, what was it, y squared dx plus x dy will turn out to be, again, as you might expect, 5/6. Why you might expect it is it's precisely negative 5/6. Namely, this is negative, make that a bit more pronounced, the orientation, or sorry, negative C1 with positive orientation, y squared dx plus x dy. So the integral over C1 negatively is negative the integral over C1 positively. Negatively and positively, I mean negative and positive orientation. Let me put all of this together. And I've got, yeah, these have reversed orientation. So, a nice theorem. The integral along, say, a curve C, and here's why I left f of xy deliberately without a ds, dx, or dy, because it depends on, or the result depends on which you have. The integral of f along C of xy with respect to x is negative the integral backwards, f of xy along x. Similarly, the integral of f of xy dy is negative the integral along c backwards, f of xy dy. However, This I won't prove. You can sort of take it on faith if you like, but it comes from the rather remarkable properties of parametrizing by arc length. The integral of f of xy ds. If you want to see how this works, definitely write me. It's pretty cool. But in any case, for the practical purposes of computation, it doesn't matter whether you integrate over c or c backwards if you're integrating with respect to arc length. So first and second, the integral over a curve is negative the integral over the curve backwards for x and y, but makes no change in sign if you integrate with respect to arc length. And here, I suppose, just to be absolutely clear, of course, I'm using the notation I established there. When I say negative c, I mean c backwards. So c is or negative c is the curve c with reversed orientation.